Let's have a look here now at the idea of a dot product. There's two ways that you can think of calculating a dot product. You can think of it algebraically or by arithmetic, and that's the first definition that you see here. Now, you could have a vector in two-dimensional or three-dimensional space. And the example, the way that it's given here, is a vector in three-dimensional space with the three components. It would exactly be the same principle in two dimensions. When we define the dot product in this way, we're going to calculate products of the first coordinates plus product of the second coordinates, and then plus the product of the third coordinates in the case of 3D, and in the case of 2D, we would just do these first two terms. That's my algebraic way of calculating dot product. And then there's also a sort of geometric way of visualizing or calculating the dot product, and that's magnitudes. Now here, in the way that it's written, when they put a single bar, this actually indicates magnitude. It's just that they use the boldface type to indicate the vector. So we recognize that it's a vector because it's boldface, and so then they'll use only a single bar to indicate magnitude, whereas if I'm writing it by hand, it's not convenient to make boldface indication of a vector. So you put an arrow on top, and then to indicate magnitude by writing it by hand, to clarify the distinction between absolute value and magnitude, we use double bars when writing it by hand to indicate magnitude. Okay, the key thing is that theta is the angle between the vectors, and that has to be identified when you put the two vectors together with a common starting point. That's where you find the angle between them. And that angle between vectors exists whether you're in two-dimensional space or in three-dimensional space, because even in three-dimensional space with two vectors, if those two vectors are not parallel, you form a plane that contains those two vectors, because then you have 3 points. And in that plane, you have a two-dimensional plane where you have in that plane the angle between the two vectors in that plane. All right, so let's see some of the things that we can do with this dot product. So to proceed a little bit further, before I move on further, I know I need to make sure that I'm going to use this. I want to make sure that it's clear what I mean by this. It says, write a unit vector in the direction of vector v. So if v was just any arbitrary vector in two-dimensional or three-dimensional space, it doesn't have to have a length 1. But what I could do is make a unit vector u that is in the same direction as v. A unit vector in the direction of v would have a length 1, because it's a unit vector, but it would point parallel. It would be parallel to v. It would point in the direction of v, not just parallel, but in the direction of v, and have a length 1. So the way to do that is very simple. You find the vector v, you find its magnitude, you divide by its magnitude. Right? So what you're doing with this 1 over the magnitude of v, is you're multiplying the vector by this scalar quantity that scales it down to length 1 or magnitude 1. So you can think of this vector u, maybe something like that, that is a length 1 unit vector that is in the direction of v, pointing exactly in the same direction as v. So I'm going to use this in the next slide. Let's derive the formula for the projection of vector b onto vector a. So this is a notation, projection of b onto a. And so that's this little pink vector here that we're actually trying to find a formula to find out what that is. And one of the things that we can use the dot product for is in breaking up vectors into these components, such as this. Like I don't necessarily want to write b as a combination of unit vectors. I want to write it as a combination of vectors, one of which is parallel to a. And that's an important tool for a lot of things later. So this work is finding a formula for this vector. It's the projection of b onto the vector a. So what would it be? what I'll do is start with, let's call this, since we're breaking up B, I'm going to think about this here. I'm going to call this B1 and B2, and I have thinking about two different things sort of at the same time. I've got B1, the scalar, that's the length of this vector, and then B1, the actual vector, which is actually what I'm trying to calculate. So the first thing I can do is just find the scalar. So if we imagine an angle between vectors A and B, I really have no use for these P, Q, and R. They're just there. So I'm looking at this vector A is green, vector B is blue, and I'm trying to project, basically project B onto A, which means find this vector that's in pink. You could even think of this like if you were directly above vector A, and vector A is like the ground in your point of view. If you were shining a light straight down, we're finding the shadow or the length of the shadow of B on A. So all that is just going to start off with trig. Cosine of theta is B1 over B, but I need to say magnitude of B. B1 here is the scalar. Right? So that means I can write B1 as magnitude of B cosine theta, and then this is a sort of out of the blue, but it works. If I multiply the top and the bottom by the magnitude of A, I won't have changed it, but I will put it in the form I need. So multiply the top by magnitude A, but I don't want to change this, so I'll multiply the bottom by magnitude A. And now if you look at that for a second, you say, oh yeah, I get it. That's why you multiply top and bottom by A, because this right here, I can say is the dot product of A and B. So if you knew vectors A and B, and you could find their dot product, let's say by the arithmetic or algebraic method, you wouldn't need to know the angle. You could just compute the dot product, and you'd have this numerator. We'd still have to know the magnitude of A. And so this is B1. This is all scalar. I should say it's the scalar B1. Right? But now, if I want to find the vector B1, where I actually mean this vector, so B1, the vector, which really is the projection onto A of the vector B, what I'll do is I'll just take that scalar and multiply it by a unit vector in the direction of A. Right? So take this scalar, A dot B, which represents the length that I want, the length B1. This is the length of B1, and multiply it by a vector that points in the direction of A, but it's a unit vector. So A divided by magnitude of A, and then hopefully readable. What I have here is A dot B over magnitude of A squared times the vector A. That's what I was trying to derive. That is a formula to find the vector projection of B on A. You can see this is clearly a vector. One of the things that I look at as I'm trying to read this is I project onto the one that's this lower subscript. So it's a projection of B onto A. Projection of B onto A. Another thing that I'm looking at is that since I have this vector A here, I know that it must be a projection onto A because it's in the direction of vector A. So the projection of B onto a vector A whether you're in 2 dimensions or 3 dimensions, is computed in this way. I mean, there could be computed in other ways, of course, but this is one way to find that using a dot product. So let me just show again the picture. I have onto the vector A some other vector B, and that what we just found is really this, like the shadow of B on A. Sometimes questions will require us to find the normal to A, this guy. You could call this B2. So B1 we found with this formula. You might think, oh no, we got to do a formula now for B2, and usually we don't need to. We don't really need to ever, because in order to find B2, if we could find B1, then we could just take B, subtract B1, and what's left is always B2. In other words, because B1, the vector B1, plus the vector B2 will equal B. In other words, B is decomposed into 2 vectors. Sometimes if we want to find B2, sometimes it'll ask for that, we can just take the original vector B minus B1 and just do that simple arithmetic component-wise, as you could say, this is a formula to find B2, and this is a formula to find B1. And so that in this way you can find both of the components of B, one parallel to A and one perpendicular to A. And again, whether it's 2D or 3D, this applies equally in both cases. Another thing that I wanted to mention is that it may happen that the vector B, when you project it onto A, it doesn't look like it's literally on A. So we use that phrase onto A, but really to be a little more precise in the wording, you might say what you really mean is onto a line that contains A. If you projected B onto a line that contains A, you may find that the component of B on that line is not necessarily going to be something you draw on top of A. Of course, you could draw this pink vector anywhere on the page, and you could literally you could back it up right on top of A and say, there it is, it's on A. But it's often, the way that we would visualize it in an orientation like this. So the projection of B onto A might mean just more precisely onto a line that contains A, or onto a line parallel to A. Because of course also in many cases these A and B don't necessarily have to be conceived of as starting at the same place all the time. It's just that you could have them starting at an initial point in order to visualize that projection. So and this slide is just reminding me to talk about how there was a distinction between a scalar value, that is the length of the projection, and then there's the actual vector, and this is boldface here, so this is really with an arrow if I was writing it by hand, because this is actually a vector. It's a vector because that's a vector. But all this is scalar. That is, it's just a real number. Something you could measure, you could find on a scale. Right? Whereas a vector is several scalars combined together, and it has many uses. If you study linear algebra, you see some very abstract senses in which we look at the concept of a vector, but through Calc 3 we look at vectors as giving us directions and magnitude for the applications in Calc 3. Alright, so let's look now at an example that we can use the dot product. And actually we don't really need the dot product for this, and we don't even really need vectors, but this is something you could solve with just basic trig. But it's a good example to begin with some basic ideas to see how the dot product and vectors can be brought into the analysis, because these principles of dot product and vectors, they take us much further than what you could do only with basic trig. Right? So Alright, so with that in mind, we have here a 1,000-pound block is sitting on a ramp inclined at 10 degrees to the horizontal. Write the block's weight as a vector and find the vector projection of that weight parallel to the ramp. Use that to determine the magnitude of the force required to keep the block from sliding down the ramp. So we have here some vector that could correspond to the weight. Let's call it vector W. The reason that we can use a vector is the weight, of course, is just 1,000 pounds, but we can put direction with that weight. It's 1,000 pounds, and it, let's say, is straight down in a coordinate system that we're seeing here. So there's more than just the magnitude of the weight here. There's the direction of the weight, which actually is a force. You could say 1,000-pound force straight down in this coordinate system. But that weight, we can actually break it up into two vectors. Let's say one vector that is parallel and one vector that is perpendicular. So if we imagine maybe one vector like this, so it would really be something like that, where W could be broken up into two components. Really, that's where the basic trig comes in. If you could find the sides of that triangle, then you could really answer the question without using dot products or even vectors. We can come back to that at the end if you want to see that, and I'll do that way too. That could help simplify just another way of seeing it. But all right, let's see. So I'm going to break up the weight vector into these two components, a red one that's parallel to the ramp and the blue one that is perpendicular to the ramp. And I can see that how those two vectors added together produces the vector W. Let's say W is W1 and W2, and this is my W1 and this is W2. These guys both are vectors. And let's figure out, well, it says write the block's weight as a vector and find the projection of that weight vector parallel to the ramp. So part of my answer will be W1, but I am getting a little ahead of the question. Just answer the first part by saying the weight as a vector. It's natural to make down here a negative and say it's 1,000 pounds, so I could do 1,000 as the magnitude and then just do negative j. So negative 1,000 j is a way to express the weight as a vector in a coordinates, in a standard coordinate system. By the way, this is just an aside. It could have been, notice that you could have done this. You could say, what angle is this vector W relative to the x-axis? It is, let's say, 270 degrees or minus 90. I'm going to use minus 90. So if I had actually gone cosine of minus 90 degrees for the I component and sine of minus 90 for the j component, this cosine of minus 90, this is all equal to 0, and this sine of negative 90, that's equal to negative 1. So that's a way of seeing, oh yeah, that actually fits with what was given earlier, negative 1j, negative 1000j, right? That's a way to see in the two-dimensional space an angle and magnitude for that weight vector. But we don't really need all this. This is something you could just do mentally. So write the block's weight as a vector. That's done. And find the vector projection of that weight parallel to the ramp. So what I need to do is, in order to one way to do that with the material that I've presented in this section, there's other ways to do it, but based on what we've done so far, what would be next step would be to actually produce a vector for the ramp itself. And you don't have any information about the length of the ramp, and it won't matter what length you use. And so a good choice here would be to just create a unit vector in the direction of the ramp. So we'll say magnitude of 1, and then use the angle of 10 degrees, because that 10 degrees is the angle in standard position. So r is 1 times cosine of 10 on the I component, sine of 10 on the j component. Now these are not special angles that we can easily get exact values for. So the best thing to do here would be to leave them as the sines and cosine of 10 degrees, so that you have exact representations for the ramp vector that you could approximate at the very end. So we'll just say this is cosine 10 degrees and sine of 10 degrees, and you could either write it this way, or cos 10 on the I component plus sine 10 on the j component, either with brackets or with the I and j, but that's the ramp vector, and the magnitude is 1, right? So we don't have to write it. So now all I need to do to use everything that we've developed in this section is just say I'm looking for the projection of the weight onto the ramp, and that would be the weight vector dot ramp vector. It doesn't matter what order I put this in the projection, because the dot product is commutative and the order, it's the same result in either order. And then I divide by whatever that vector was I'm projecting onto, its magnitude squared. And then I multiply by the actual vector that I'm projecting onto. But remember, the magnitude of r, the magnitude of the ramp vector, that's 1. So that greatly simplifies this calculation. It's just 1. Magnitude is 1. Magnitude squared is still 1. So this amounts to just finding the dot product of w and r. And then multiplying that scalar value by r. So let's put w, could be written as 0, negative 1,000, r, cos 10, sine 10. This is all scalar, and it's times r, and I'll just write r partly because that's all the space there is. So I just do a dot product here. 0 times cosine of 10, well, that's 0, plus negative 1,000 times sine of 10. That's the dot product, and that's multiplied by the vector r, which was cos 10 sine 10. So I have a scalar that I'm multiplying by the vector to produce a vector. So to leave the answer in an exact form, it's 1,000 sine 10 degrees times the vector cos 10 sine 10. Now, without the negative, that's the magnitude of the force. So that's the most reasonable way. I mean, actually, this is a word problem. So really, the thing that I would do is to put this into decimal. So let's say this is about negative 173. I would put this in decimal because it's a word problem, because it means something to write it in a more practical form, right? But then I might, so this is 173.6 is the magnitude. The negative is part of the direction. It's convenient to leave it there. I'm going to leave this as it is for a minute, just to say that I think I will interject also here a comment that a certain pattern that we will see often in dealing with vectors is that we can identify a magnitude, 173.6, and we can identify a direction vector. So this is a direction vector. This cos 10 sine 10 is a direction vector. It is pointing in the direction of the ramp, up the ramp. This negative is what reverses the direction of the vector so that it's pointing down the ramp. The component of the weight that is going down the ramp, and it's specified by its magnitude and a direction vector. And still, one further point about that is that this direction vector is a unit vector. That's the very frequent thing that will happen as we move forward. A magnitude and a unit vector that specifies direction. I can tell unit vectors when I see cosine sine, because I know that cosine squared plus sine squared is always going to produce 1. So the magnitude is 1. What I have here is, I know that it's 173 pounds of force in the opposite direction of the ramp vector. That's W1 that I was trying to find. Right? Ramp vector is here, right? That would be the ramp vector, and W1 is in the opposite direction of that ramp vector. So we could say what we just calculated we were calling W1. And so I could say the magnitude of W1 is just the 173.6. And because I know the context, it's 173.6 pounds of force, and that's the force that would be required to keep it from sliding, keep that block from sliding down. So we'll go back to the question again. Find the vector projection of that weight vector parallel to the ramp, which I've done, and use that to determine the magnitude of force required to keep the block from sliding down. So that's what this is. Now I suggested that it might be possible to just answer this with basic trig, so I'll try to see if I can do that. Let me just go back to the picture. Okay, well, I guess actually to explain the trigonometry of it, I really need the whole picture. It's easier to keep straight everything. And actually, this is one point where I could say it's actually kind of helpful, maybe for my explanation anyway, to move these vectors. They're still the same wherever I put them. So let's just move this a little bit. So these vectors haven't changed, but now I can reason out what the sides that I know, what side I know, and what angles I know in this triangle, so I can finish the trigonometry. So I know that the weight was 1,000 pounds, so we can make this side 1,000, this side of the triangle. And since this is 10 degrees, I have another bigger triangle here that I could say there's a 90-degree angle here, because this is perpendicular to the ground. And if that's 90 and that's 10, this guy had to be 80 here. This is 80. And if that's 80 and this is 90, then I can do some right triangle trig to figure out whichever of these sides I need, which is actually the W1. So we could say W1 is the adjacent side of a right triangle with a angle of 80 degrees. We could say, how about write it like this? The cosine of 80 has to be the adjacent over the hypotenuse. W1, the scalar value, or we could say the magnitude of W1 over 1,000, the opposite side to the hypotenuse. So magnitude of W1 has to be 1,000 cosine 80. That's 173. That's got to be 173.6. And then if you wanted to actually write the vector, you could just say the vector W1 is this magnitude 173.6, and then times a vector that is opposite to the ramp vector, or you could say, but you'd have to get this. You can't use the angle 80 directly, because 80 is not an angle in standard position. So an easy thing to do here is I just know it has to be opposite the ramp, so I can get right to a conclusion to just say negative cosine 10 and negative sine 10. What I'm doing there is just saying that's the ramp vector, and I'm just putting negatives to get the vector in the opposite direction. So that was the answer that I had before for W1. All right, so that's it. I hope that's been a helpful video.